So today I'm going to be talking about performance in Compose, some useful tips that we got when we were optimizing things in a lazy layout in particular. I wanted to note that this talk in particular gonna help with the performance in lazy layouts, but is more about general performance tips and not only strictly restricted to lazy, because it's more about how we internally optimize our layouts as well, what kind of guidelines we have, and what kind of tips we usually try to give to our coworkers whenever we're kind of trying. Sorry, a bit up? Okay, thank you. All right. So to start things up, the first thing that is interesting about Compose is that we've been focusing on correctness for quite a while. So Compose is out for like 3 years now, I think. And for the first year and a half, or maybe even longer, the Compose team was working on actually catching up with the views, because it turns out it's kind of really hard to re-implement UI framework from scratch and catch up to 10 years of development that was done in a classic view system. We still kind of catching up, but right now we started focusing more and more on performance. It's worth noting that, to be honest, like from the start, we had some potential bottlenecks. So we had some ideas where we could optimize things. For example, many things in composition and slot table are really smart and kind of optimized for the particular way how we can to perform updates and insertions quick. But as we going along and people start to use Compose in production in different ways, we realize that some things that we've been optimizing for are still stand, but there are some other things, some other bottlenecks that we could also optimize away. And that's what we've been doing for the last year and a half, I guess, in Compose team. Some of them it was like in our layout, some was more in a higher up code, like in a libraries and so on. Just doing all of this work. And how are we doing now? So I ran a quick benchmarks. Well, only one of them. The second one was already run for me, helpfully. So I basically measured how much time we spent per frame in one of our sample apps that we have in a Compose sample script. And going from version to version, you can see like steady 20% improvement in the frame time for scroll performance in particular. Scroll performance for me is more interesting because I work on lazy layouts a lot, and that's the metric that we optimize most of the time. There are a few more things like a startup and other things. Some of you maybe saw a talk from Tomasz yesterday, or Ben Weiss. They talk about some of those things as well, how we can measure stuff. So my first performance tip is to use the latest Compose version. And you kind of, when you do that, you kind of get some performance for free, basically. Well, it's not really for free, because you have to still update Compose, and it could be harder for some projects than the others. But at the same time, you don't have to change anything in your components, composables, or like how you do stuff in Compose, which is really nice. You just like update the version, assume like everything works, and you get a bit of the performance boost. But let's say you updated to the latest Compose version, and you still have some problems. So what do you do next? Well, the next you start to measure. You could write some benchmarks, or maybe you just open your app and just capture some traces from Android Studio Profiler, and you get some results, some ideas of what's happening during the frame of your app, what happens during startup of your app. And for that, the important things are to always measure release mode, enable array, and use baseline profiles, especially if you measure the app startup, because it helps. Baseline profiles helps with app startup immensely. I wanted to add some numbers to all of these things, how much of a difference you might get. And if you go from like debuggable to release mode APK, you get like a roughly 4x performance boost, especially because Compose has its own thing. It's adding a debug mode for beta inspections and so on. But also the runtime itself optimizes APKs in a bit different way. Then if you enable array, you get a bit smaller performance boost, but you get way smaller APK, because it's kind of majority of what array does is kind of optimizing for the smaller code layout. But while doing that, well, it's removing some of the instructions or like optimizing how functions look and what's not. It also optimizes number of instructions we have to run, which kind of makes sense, like optimizing for size, but also optimizes for performance a little bit in that sense. And Compose also leans on array quite a lot in some cases, for example, for lambdas. And it's kind of really important for us so that the rate is there. And the last thing is about baseline profile. So this is like somewhat new thing, I guess, for many people because we didn't have to do it before switching to Compose. Like views are in the framework, they're already pre-optimized for you. You don't have to care about it as much. With Compose, it's kind of a standalone library. So you can update it without Android being updated, which you get free performance when you update in Compose, which is great. You get new features and so on. But if you don't use like baseline profiles and don't pre-optimize the APK, you get a lot of just-in-time compilation activity. So basically, we run it like in a slow mode, and then try to optimize functions as we go. And this is really slow. It's like constant GC activities. Like if you ever work with some things that draw every frame or do something every frame, and you have garbage collector checks, it's usually slow down it up quite immensely. This is somewhat similar because it kind of has to optimize the methods in the background. So it's like basically takes the method, optimizes it, and then stops the work, replaces the method with the optimized one, and continues as it goes. So yeah, we can do this work ahead of time when installing the app, and you get the performance boot out of this. Right, so you did all of that, and you still have some slowdowns. So what can you do next? So the first section, kind of the first thing I want to talk about performance is about frame phases and how you can master them to make sure that you do just enough job to update the things that you have on the screen, like some UI components. It goes from this scheme that we usually use to represent like composed frames. So we go from a composition where the composables are run. Those composables, they create layout nodes. And then we have measurement, placement, like determining layout size, placement, putting things on the screen somewhere, and drawing the contents of those layout nodes. The interesting part about this, and the big thing that kind of changed from coming from the view world to the compose world, is we kind of, before we used to separate creation, like instantiation of the views, and their update. And compose doesn't really do so. It's kind of more declarative and kind of it was made that way. That's what I want to say. But anyway, it kind of works as designed. And interesting part about this is that now we configure everything kind of through modifiers, because you get this kind of flexible API where you just like create custom layouts or some kind of layouts, and then you tinker with like sizes, backgrounds, and all of that through modifiers rather than fields in the view. And these modifiers are mostly set up in a way that you need to update them from composition. And this is kind of this gets a little bit in the way when you try to do optimized updates for certain things. So as you probably know in Compose, majority of the updates, well, actually all of the updates are driven by states. And that means that depending on where the state is read, it's going to invalidate this particular section of the frame, basically, if you change the state. So for example, you read it in composition, you change the state, it's going to invalidate it composition. Then you move it to measure, for example, and then you don't invalidate composition anymore. You don't do that work. And later today, we're gonna look at how to do this actually. Yeah, similar thing happens with draw. If you have modifier.background or something and you're animating it, you probably just want to do that in license. So yeah, the perf tip is to defer frequently change states in later phases. The interesting part here is that, although I'm saying that we kind of want to move certain updates to later stages in Compose frame, we don't want to move all the updates here. That's why Compose was designed in a way where actually perform a lot. Whether your composition is completely fine. And there is a little bit of the cost when you defer the states. We'll see how it is done, and I'll discuss why it's important a bit later. But right now, let's go into some examples of what we can do. So let's say we have modifier.size, and we want to animate that size. For example, here we have a composable. It takes a size, some kind of integer. We animate it as state. So basically, if you change the integer from one execution to another, it kind of slowly animates in one size to another. Here we read state in a composition, and we invalidate the composable. I think this composable is just going to restart in itself, but at the same time, we still need to run all the machinery to run this recomposition. And yeah, we invalidate, and by that, we also invalidate in the rest of the frame as well, so it's like quite a lot of work done here. Right, so the question is, what can we do here? There are things like modifier offset that kind of don't do exactly what size does, obviously, but it has like this lambda-based API. And as I was saying, lambda-based APIs allow us to do what we actually want. We basically read the state in whatever phase lambda is executed in. And if you read the documentation of the offset, you see that it's actually executed in placement. It's invalidates placement and draw. So we kind of want to do the same, but for size. The reason why we don't have it by default in Compose is that we are being really careful with the modifiers that we kind of move towards this lambda-based API because it has its cost. Like lambda is not free. Lambda is an object that you have to allocate during runtime. If it has like some captures, you maybe have to remember it to make sure that when you recompose it, it's not created again. It does not invalidate all the modifiers. So it's like lambdas are a bit complicated there, and although there's a bit tempting to move everything to lambda, we try to only do it for modifiers that are actually likely to update frequently. But we have a bit more generic APIs that kind of allow to do roughly the same thing. So for example, here you have modifier.layout. It's somewhat generic modifier that allows you to affect layout of particular node. So if you have written custom layout in Compose, it's kind of the same thing, but instead of getting one measurable, multiple measures as your children, you get measurable for the node that you propagating this modifier to, you get the constraints that it should be measured with, and then you just basically do measurement and placement. And depending on which of the stages here you read the state, it's going to invalidate like different passes. So if you read it where we measure, read it in a block where we measure things, so the state is going to invalidate on measure, placement, and draw. But if you read the state in the block that places things, it's only going to invalidate placement and draw. Right. So let's use this modifier to create kind of lambda version of the animated size. So before we had this, now we replace it with the modifier.layout. So what I do here, I kind of update the constraints to this fixed size that we want to animate things to, and use the size to measure the placeable. And by doing that, yeah, we read the state right here. It affects this block, and this block is basically only read and measure. We don't invalidate composition by that. You can also like use this built-in block for some of the modifiers that you don't have by default in Compose, but just want to create and make sure they're kind of lambda-based anyway. Just extract it in a separate function and use it across your code base, because if that affects your performance, that's obviously what you should do. Let's talk about another example, modifier.background. It does roughly the same thing. So I changed the function to animate color instead of size. So now we have a thing which doesn't really affect the size or layout of the component. We only care about like the background size. And yeah, as we read state, the one that we animate, we kind of invalidate everything again. For that, we can replace modifier.background with modifier draw with content or modify draw behind. I guess draw behind is like a bit less wordy version of this, but draw with content is a bit more generic because you can basically position where you draw the content of the node and where you draw the rest of the things that you want to add in this particular modifier. And here I just draw a rectangle behind the content. That's kind of exactly what modifier.background does. And I read the state in this particular lambda, which only invalidates draw because draw of content only executed in a draw phase and not in composition. So I ran a few benchmarks and kind of check how much time we spent on a frame. These benchmarks, the numbers are kind of relative, so I wouldn't look into absolute numbers way too much because they are executed on a really low-end device. Like majority, it's kind of 10 times faster on Pixel 7, for example, than this. So but it's still really useful for comparison. And as you can see, measure is kind of 3 times faster. That invalidating only measure placement to draw, and not invalidating composition is 3 times faster than invalidating composition. And then if you get to draw, you get like 10x improvement, like for modifier.background in particular. So like your frames are much faster. You spend less time running extra work on the frame. You have more time in the frame to do meaningful work. For example, update lazy list items or something like that when we scroll. Another part I wanted to mention, which is probably more important for people who like write their own kind of reusable components and like design systems and other things, is that you can actually test for invalidation. So here I have like a UI test, instrumented test with the compose rule. That what it does, it takes a modifier.composed and a counter. It basically checks how many times modifier.compose was executed. You can do similar things, obviously, with the layout and draw modifiers that we discussed previously. This kind of allows you to have this kind of things on this, have this test on the CI, and make sure that all of your updates don't actually, all of your updates to the component, like to the code of the component, they don't actually change how your component is invalidated. So you just have to define how it is done, and then you get the somewhat meaningful test for that. We use tests like that for lazy list, for example, to make sure, because like, it's really complicated, has really complicated relationships with measurement and composition, and we want to make sure we don't invalidate composition by accident. All right. So the second thing I wanted to talk about is derived state. So derived state is this primitive that we have in the compose runtime. And what it does, it kind of takes an expression, some kind of lambda, and then if the state in the lambda changes, but the result of the lambda doesn't change, it kind of re-executes it, but if the result of lambda doesn't change, we don't invalidate the scope where it's written. So it kind of allows to kind of cache these invalidations if we know that the result is not meaningful. And I plug it in the same benchmark and measure, and you see like we have derived state when it's when the result of the expression is not changed. We're roughly on the same pace as measurement, which is really good for derived state because it's kind of complicated what it does internally. But if the derived state expression changes and actually validates the scope, in particular here I was reading derived state in composition, probably should have highlighted that. But anyway, so if derived state actually invalidates composition, we get quite a visible slowdown. It's not that big, to be honest. Like this device obviously has like bigger deltas, but it's still a bit slower than that. So derived state has its own overhead. And the problem with many of the derived state usages is that there are people basically create some kind of expressions that change the derived state result pretty frequently, almost as frequent as the state result state that it's read into. And you don't get any benefits, you only get the slowdowns from the derived state because of that. So a few examples how it can be done. So this is like the simplest one, which is like, it's really stupid on the slide, but when it's like in the composable code, you see it, and it's like inside your components code, you might just oversee it for some reason. So here we create a state which has an integer value in it, and a derived state returns this value multiplied by 2. So derived state doesn't do anything meaningful thing here because like every time you change the integer, the result of the derived state is going to change as well. No caching, no kind of preventing invalidations, nothing like that. You just pay the cost of the derived state without getting all the benefits. Similar things happen with the lazy list. So you get like some warnings, I think. I don't remember the version, but there are some warnings attached to lazy list state fields. It's like first visible index, the first item scroll offset, I believe. And one of the workarounds for that is to wrap it with derived state. But you didn't fix the warning. what happened on this slide is just basically we create a derived state which is even slower than the original expression was. And instead, you probably want to do what I did on the first slide, and just like check for some more kind of less changing expression. Just make sure that return value of the derived state changing less often than the inputs that you have in it. Another important fact about derived state is that you want to make sure that the results that it gets can be compared, because we just run like equals on the result. And if they changed, we do certain things in there. And for example, in lazy layout, visible items, they don't really have meaningful equality in there because they change offset where the positions pretty often. So I think we don't even implement equals on them just for this reason, because like you don't really want to compare them anyway. But yeah, as you can, like as these values actually changing, you also invalidating composition, because when we compare it with the old value, it's never the same. Right. And the last thing about states in particular, I wanted to kind of go into this, go to this node provided, I think, by Jeff Dean. So it's kind of it's a node with approximate numbers for like memory access, disk access, and like network. So you can kind of choose your algorithms when implementing things. Like you know that, for example, network access is like 10x slower the disk, and then you probably can cache something on the disk on the memory and get like some performance that way. So I wanted to do similar things for Compose, and it turns out what my teammates wanted to do this too. So we kind of ran some benchmarks. So what we got is for regular JVM things, like what you do in Kotlin is like local variables and functions. It's around 1 nanosecond. We don't really actually know exact values here. It's like all approximate. Specifically for the smaller values here, we don't know because the the range that benchmark had measures around like 8 nanoseconds. So we don't really get that. But like if we measure it multiple times, we kind of get somewhat a cumulative result. So this is what we get. So local variable read in function, like function parameter or something like that, is really fast in like somewhere in the register. So you get like 1 nanosecond. Field read, you have to get the instance of the class and kind of go somewhere. So it's like 5 nanosecond. Then you have like virtual method call. In particular, like you call a method on the interface. That's a bit slower. Then you get synchronized reads. So it's a read that rapidly synchronized or something like that. We use it in Compose again quite a lot. It's a bit slower as well, 15 seconds, just because you have to lock the thread. And then map.get is even slower because it does multiple of the previous things. So we did the same, but for the state access. And as you can see, this like order of magnitude slower than all of those things. So basically accessing states and reading value from it has a visible overhead, because we have to record where the state was read in case we need to invalidate the scope. So this in particular is read in composition. So yeah, you basically get like somewhat visible slowdowns if you if you have some kind of measurement or some composition block and you write derived state, or you read derived state in a loop, and it kind of adds like a little bit of overhead here and there. And like in lazy list, at some point we were reading it like 2 or 3 times per usable item, and measure was basically dominated by derived state reads. We're obviously optimizing this, and we also like derived state itself. We optimize this as well by moving derived state read into like only being read once at the beginning of the measure, and then continue use at least cache variable, because as we saw in the beginning, class field read is quite fast. So that's what we do here. So yeah, you might be feeling right now it's like derived state is really bad, like shouldn't use it. And it's not really the case, because derived state still does save some time. So as you saw in the beginning, if you use it right and actually make sure that the return value is the same as the previous one, you get meaningful speed up, and you're still allowed to invalidate composition at the same time. But sometimes it's actually better not to use it. So like, for example, here, we can just replace it with lambda or just read value directly there. And the same with the kind of state holder patterns where we have like a state things. I saw people sometimes just not export as well, but like make public API that kind of just takes a private state and calculate something in the derived state of, and it's just better to have a simple getter in there because like you don't pay price for both state access and derived state access, only for state access. All right, so this is derived state. And the last thing I want to talk about the case of initial composition. So we've been talking a lot about how to avoid things in the first section, how to avoid composition updates. But initial composition is actually a case where composition cannot be really avoided because it's in the app startup. You need to create all of the things you're going to show on your screen. Or if you're replacing one component in another, like if you have if else in your composition list, you have to remove the previous one and put a new one in there. So kind of like still execute your composables at least once before we can skip future updates. And lazy list also does quite a lot because every time you scroll, an item can be reused. We reuse internal structure, but we still run the whole composition because we want to make sure that all of your remembers, so your launched effects, are re-executed again for the new item that is now visible. And in composition, well, in Kotlin as well, but both compose and Kotlin primitives, they have some cost, some more than others. And generally, the closer you get to JVM, to like usual classes, fields, methods are not that expensive, but before I get from them, like some of the things in coroutines or some things in compose can be getting a bit more expensive. As we saw with states, for example, state reads was like 100 times slower than reading field from class. So, what I noticed, and I was also doing this quite a lot, still doing it, is like we rely on a compose to kind of define most of the states of the component. And we also use it for kind of synchronizing the life cycle and kind of launching all of the operations right inside our composables, like using a bunch of launch effects in one place and then just like spreading the state through the members and so on. But composition is always on a hot path in a way because it's usually somewhere, it's usually like something that you have to show, for example, on a startup straight away. You have to execute composition to get what you're going to display on the screen. And similar things with the lazy list, we kind of have composition during scroll, which is kind of a real also really time sensitive place to have composition. So in a way, we want to kind of try to optimize things. So this is a really complicated component I took from our code base. I simplified it a bit for the slide. So let's quickly go what's happening here. As you can see, you have like multiple remembers and launched effects. So the first one is we have an interaction source. Interaction source is this kind of, it's an API that allows you to subscribe and update on like if the component is pressed, if it's focused, things like that. And then with the interaction source, we also have currently active invalidation. So, active interactions, yes. Basically, if we currently pressed or focused and so on. First launch effect collects the interaction sources and updates active interaction lists with like currently active interactions. And then we use those currently active interactions to animate color to some state based on the configuration. So you have like a themed value, a theme configuration, and you use that to define pressed color, focused color, and somehow animate between them basically. And configuration can also change. It can be like composition local or something like that, and you can switch from like light theme to dark theme, and we also have to update that, so we use it to update. So yeah, right now we basically have multiple remembers and multiple launch effects that do something, and this is pretty slow. And my first tip is kind of lean more into Kotlin because we were learning a lot how to compose things work and what idiomatic compose means. And sometimes I feel like I'm personally leaning into it too much, doing too much work in a compose that I can delegate into Kotlin. Let's see what we can do here. So for example, we have multiple remembers. Kind of this is state that is spread across the composable. We can just use the state holder to move it up. And now we have basically the same thing, but we only use single remember instead of multiple to minimize, to just keep the state of the component here. Going further, we can simplify our launch effect. So all the logic that previously was in launch effect, we can move it in the simple kind of composable, simple suspendable function launch multiple coroutines there, it will have the same life cycle as launch effect does, because coroutine scope going to cancel these launch effects because of the structured concurrency, which is really useful here. Also, if you look at how we propagate the updates, in particular here we first update the interaction to latest active one, and then we subscribe to update to this active interactions list through the snapshot flow. It's also kind of wasteful. We don't need state for that. We can either use mutable state flow or just combine it into single collector, which is, we could do it before with the single launch effect, but I just noticed when I was refactoring that we actually can do that. In any case, so now we have like one coroutine for launch, but we also have to update config. So right now it's just like a mutable field. We can replace it with the mutable state flow and collect that. So it's basically linear, and by doing this, we can simplify our composable quite significantly. So we have single remember, by launch effects to collect all of the interactions and all of these things. And then I just update mutable state flow in a side effect, and mutable state flow has the thing where it's when the value that you update is the same as the previous one, you can it just discards that update basically. It doesn't invoke the update of the collector, so it's pretty great for us. That's exactly what we need to have, and that's what we had before. I also measured kind of updates, kind of performance gains that we gain if we just like use a simple box as a component below all of this, and you get like 9% improvement above time in the frame and allocate time to compose and allocations that you use when you compose and things. This is pretty nice for kind of the simpler refactor. And state holder is also a bit more flexible in how you can do things with that. You can also move things to private API, expose a better API for components, and so on. So this is kind of a bit more, it feels intuitive pattern to use when you wrap your head around compose. And an interesting thing about all of that is like modifier node kind of does the same thing. So I don't know if you heard about modifier node, but it's like internal rewrite of the modifiers. And it's also leaning a lot into the fact that we don't really want to do a lot of things in a composition. We kind of want to move, just create some kind of classes and some stateful object, and like in regular Kotlin, and just like remember that single object instead of like creating multiple states, coroutines, and different things in there. All right, so this is actually it for my talk. So what we learned today, the first thing is kind of mastering the frame phases. You want to be mindful where you read frequently changed states. It's all right to recompose here now and then, but you need to make sure you don't do it in every frame. And if you do it every frame, at least you need to make sure that it's not recomposing the whole world. But hopefully some of the tips with modifier.layout, draw with content, and how to test for that would help you to move these things there. So derived state is, as we learned today, is kind of complicated. And we all have complicated relationships. Well, at least I do have a bit of complicated relationship with that. So we need to make sure that we provide their cacheable values that don't change as often as the states that you read in it do, so that actually give you some meaningful optimization instead of like just paying the cost of the overhead of the derived state and not getting any meaningful thing out of it. And yeah, likely you don't need it, so kind of think about every usage of the derived state that you have in your code base really carefully. In composition, we want to make sure, like right now, the main thing that Vera composes first is actually initial composition. We obviously will be optimizing a lot of these things in the runtime and compiler itself. But at the same time, you can also optimize your components to kind of group up some of the work that is done there. And kind of don't overuse compose and some of the Kotlin primitives, and just kind of think carefully, especially if you're designing something like a reusable components that you have like an design system and things like that. And one thing I didn't really touch on the slides, but is also quite important, is to defer setup until it's actually required. So like if you have something that you set up in your composition, for example, the things that we have in a modifier, we used to have in modifier.clickable, we kind of launching all the coroutines straight away when composition started, instead of waiting for the first touch input that happens there. It's like most of the buttons don't really click, so like we just launch a bunch of coroutines without doing any meaningful work. So yeah, this is kind of like another small thing that is really important. So what's in there for us? Like, what's the future work at Webinar? So obviously, we're gonna do more compiler optimizations in the initial composition thing. There is also experimental new stability mode that recently landed. Bencher and Grove did majority of the work there. We will basically allow skippable and restartable functions with assembly value in this mode, but it has some caveats of how things executed, which your app might depend on. So right now it's kind of experimental. We'll be talking about this more, I think, in closer to 1.7, like after current stable release, because we don't want to break current stable release within more unstable things. Yeah, we'll also be writing a lot of things in the composer runtime and optimizing things in there. State updates and state reads in particular, one of the things that I personally was looking at recently, and we got some meaningful performance there as well. And then we'll also look into the components that we have in the foundation, in the UI, in the material, and like all of the things that kind of we provide. And we try to optimize that as well, and kind of applying all of these guidelines and more of them to those components, because this is the thing that everybody uses, and we want to make sure those are also fast. And the last thing for us, hopefully, we get more of the debug and benchmark tools that you can use, some kind of simplifying some of the setups for you, or maybe giving you more information. I cannot give a lot of promises here, because it's like there's different things in the work, but you can follow some of the Android Studio updates in particular and see what's in the next releases. All right, that's it for me.